Hi, Calc PC. Welcome back. We're talking about a new integration technique. And this one is a very nice technique. When you recognize that it can be used, it can certainly save a lot of time, as we're going to see here in just a second. So it's called partial fraction decomposition. And basically, what we're going to attempt to do here is take a fraction and split it up into a couple of smaller fractions that are a little bit easier to integrate. And so I want to start by showing you an example that we could actually do with the technique from last time, the trigonometric substitution. Um, it's right here. And as you look at this, you might be thinking, well, gosh, yeah, that certainly does look like something that we could have done with our part. I mean, sorry, with our uh, trigonometric substitution. All we need to do is complete the square like we did on the previous problem when we were doing the homework yesterday. So let's take a look at how we could complete the square here so that we could then use one of those triangles that we had talked about yesterday for that. So what would we love to see added right there in the parentheses that would make this a nice perfect squared trinomial? Okay, so again, you look at your b 5 and you cut it in half, 5 halves, and so and you square that, and so you get 25 fourths. Okay, and since we're adding 25 fourths, we will simultaneously subtract 25 fourths. And sure enough, that's a nice binomial squared now. And we get x minus 5 halves squared plus, well, 6 minus 25 fourths, that's actually negative 1/4. So actually, I guess we'll make that a minus. Yeah, it's negative minus 1/4. And so now we have ourselves a u squared minus a squared antiderivative here. So it's going to be the u squared minus a squared idea. And so when we go back to that triangle, we know that that is the third one of the triangles, so that, as I introduced them previously. So in this case, u is our x minus 5 halves, so that will equal 1/2 secant theta. And the square root of u squared minus a squared, we don't actually have that in the denominator. We have that squared, right? And so remember, the square root of u squared minus a squared is a tan theta. So in this case, the x minus 5 halves squared minus 1/2 squared is equal to 1/2 tangent squared theta. So I'm sorry, 1/2 squared as well on that, tangent squared theta. And let's go ahead and make that substitution. Oh man, sorry about that. It's supposed to be an integration symbol, didn't turn out very good. And you can see for dx, I'm going to get 1/2 secant theta tan theta d theta. And in the denominator, we're going to get 1/4 tan squared theta. And 1/2 over 1/4, that's going to give us a 2 out front. And if you take secant and divide it by tangent, okay, remember that's 1 over cosine divided by sine over cosine, you basically get 1 over sine. So that's cosecant theta d theta, which is, of course, a fairly straightforward integral. That's just 2 natural log cosecant theta minus cotangent theta. Oops. Started saying cotangent, and then I started writing cotangent. Darn it. Cosecant theta minus cotangent theta. And you know, we would have to go back to the triangle and figure out what cosecant and cotangent were. Um, I'm gonna save us having to go back to that and just tell you that that's the cosecant turns out to be 2x minus 5 over the square root of x squared minus 5x plus 6 times 2. And the cotangent turns out to be 1 over that same square root. Like so. All that, of course, has a plus c. And there you go. It does simplify down. There's some simplification that we can do there. But you can see that it's going to take a little doing there with that simplification. So what partial fraction decomposition says is, okay, yeah, we could do it that way. But if you were to recognize that 1 over x squared minus 5x plus 6 is equal to 1 over x minus 3 minus 1 over x plus 2. Sorry, it's a plus 6 at the end, so that's got to be a minus 2 there. Wouldn't that be a lot easier to integrate? If we could take that fraction and decompose it into these two, gosh, that's a whole lot easier to integrate, right? Those are both just u prime over u's. So this is going to be the natural log x minus 3 minus the natural log of x minus 2. You know, done. So the trick to partial fraction decomposition is, how did we get here, right? How do we know that 1 over x squared minus 5 plus 6 is equal to 1 over x minus 3 minus 1 over x minus 2? That's the partial fraction decomposition part. Okay, so let me show you how they did that. What you do with a partial fraction decomposition is the original fraction Okay, we know what the factors of the denominator are. This is factorable. That factors into x plus, I wanted to say plus again, I know it's minus, x minus 2 and x minus 3. So I'm going to pretend I don't know what the numerators are. So I'm going to say, hey, that's a over x minus 2 plus b over x minus 3. Okay. And now what I'm going to do is I'm going to solve for a and b. And here's how I'm going to do that. I'm going to multiply by this denominator. Let me change my color here. I'm going to multiply by x squared minus 5x plus 6 to move it to the other side. But when I distribute it, okay, the left side would just get the 1, right? These will cancel. When we distribute that, well, remember, one of the factors of x squared minus 5x plus 6 is x minus 2. So we get a times the remaining factor, x minus 3. And when I distribute here, one of the factors of x squared minus 5x plus 6 is x minus 3. So I get b times the remaining factor, x minus 2, like so. And now all I have to do is solve this for a and b. And I'm going to do that by making a convenient choice for x. What would be a really convenient choice for x? Oh, I don't know. How about x equals 3? Because if x equals 3, then you get 1 equals a times 0 plus b times 1, right? 1 equals b. Okay, so 1 is equal to b. What would be another really convenient choice for x? Oh gosh, I don't know. How about 2, right? Then you get 1 equals negative a, and then the coefficient for b turns out to be 0 right there. So a is negative 1. So I can come back to my original fraction and say, Gotcha. 1 over x squared minus 5x plus 6 is equal to a, negative 1 over x minus 2, plus b, positive 1 over x minus 3. Now, I'd written it in the other order in the previous slide, but that's exactly what we used when we went to do this integral. It's really nice because, if you think about what happened on the first problem, remember how I said, I kind of glossed over it. I said, oh, well, there's some simplifying you can do here. Yeah, there is. You know, these terms can be added together, and then you can use your properties of logarithms to split it up. Okay, and I guarantee you, though, at the end, you will get natural log of x minus 3 minus natural log of x minus 2. And that could, of course, be written natural log of x minus 3 divided by x minus 2. Let's see. Use the properties of logarithms. So we condense it down all into one nice compact logarithm. But you're going to have a lot more work to get there, going through the trigonometric substitution phase. So that's what partial fractions, that's how it works. Now, a couple of things about the one we just did. It was very important that my factors, when I factored my original denominator, they were linear factors. That's why I used constants. I used a constant a and a constant b. Okay. If the factors are not linear, okay, if there's, say, quadratic factors in the denominator, then you have to use a linear factor numerator. You see, you're always trying to decrease the degree for the numerator by 1 power. I guess I should say that's if it's a unique quadratic factor. Okay, and what do I mean by that? Well, I'm gonna show you what happens if we have a repeated linear factor here in a minute. And repeated linear factors can be treated a little differently. It's okay if you forget this part, because in the end, it still works out. But I just know that it's a little easier to set it up if you remember, oh, that's a repeated linear factor. My integral this time is 5x squared plus 20x plus 6. All of that is divided by x cubed plus 2x squared plus x dx. And so what I like to do is kind of come off to the side, do a little scratch work, figure out what the partial fraction decomposition is, and then come back and substitute it into my integral. So I'm actually going to go, if you need to write that down, pause the tape here, or tape, video, whatever. I'm going to come over here and break that thing down for us. So let's see, it's 5x squared plus 20x plus 6. And that denominator is x times x squared plus 2x plus 1. Okay, which of course that quadratic is in fact factorable. But you can see it's actually a repeated factor there. Okay, and so when we have the repeated linear factor like this, we're going to do a slightly different partial fraction decomposition here. What we're going to do, say, okay, well, obviously we have an a over x because there's just a plain old x term. There's obviously x plus 1. But because it's a repeated factor, x plus 1's quantity squared, I can still use a constant numerator, even though that degree in that denominator is a square. Okay, because normally with a squared, we would have to use a linear term numerator, and I'll do an example of that here in just a sec. So this actually helps us quite a bit, because now we still are just looking for 3 constants, and there's no linear factor out there. So I will do the same thing. I will multiply by the denominator over. So 5x squared plus 20x plus 6 will be left alone. And when I multiply the denominator over here onto this side, okay, well, for a, the x terms would cancel. So we have x plus 1 plus 1. For the b, one of the x plus 1 terms will cancel. And for c, similarly, the x plus 1 terms will cancel. And so we'll get just cx there. All right. So at this point, we're going to make the same idea that we had before. Pick a convenient choice for x. Well, gosh, you don't get much more convenient than x equals 0, right? So if x equals 0, notice on the left-hand side, that's why it's so convenient. The 5x squared is 0. The 20x is 0. We just get 6 equals, well, if x is 0, you get a times 1 times 1. We get a. B times 0 times 1, and c times 0. Those drop out, and look at that. We're sitting pretty with, we've already solved for a. If I make a convenient choice for x again, okay, x equals -1. Well, then I notice that the left side is not quite so easy, right? You have 5x squared, so there's 5, minus 20 plus 6, so you get -9. Now, if x is -1, you get a times 0, you get b times 0, but you get c times -1, so that's -c. And so c is 9. Now, what you may be noticing is like, hey, coach, we're out of terms here. You know, we've made all of our convenient choices, and that's true. I would suggest that maybe you pick another convenient value for x and use what you've already solved for. So what would be a nice easy value for x? Well, you're probably thinking +1. And that's a good idea. Because if x is +1, the left side is just 31, right? 5 plus 20 plus 6. Okay, the right side, well, notice we get 2 times 2 times a, so we get 4a. We get b times 1 times 2, so we get 2b. And we get c times 1. Okay, and now we can use the fact that we already know a is 6. We know that. We solved for it already. We don't know b, but we know c is 9. And so putting that all together, okay, well, we can see that that's 33 plus 2b. Well, we'll subtract the 33, and we'll get that -1 is equal to b. Oops, there we go. So hopefully that made sense, how I was able to solve for that third one. This is going to happen a lot, where you're gonna have the convenient choices, and you're going to be out of convenient. We're out of the super convenient choices because we've made things drop out, but we've already solved for some of them, so we can continue to use those as we make other convenient choices for x. Let's go back. We now know. Oops, sorry, I didn't mean to do that. That this is equal to the integral of, well, remember a was 6, so over x. B was -1, so I'm just going to put -1 over x plus 1. And c was 9. Like so. And at this point, we're ready to do our integration. Obviously the first two are this is 6 natural log of x minus the natural log of x plus 1. And then this one with just a little bit of u substitution, right? You let u equal x plus 1, du is equal to dx, all that stuff. So we'll add 1 to the power and then divide by the power. So we'll make that -9. And yeah. this is natural log of x to the 6th minus the natural log of absolute value of x plus 1 minus 9 over x plus 1. And let's just condense these last ones together. And we'll add r plus c at the end there for good measure. So really nice, nice technique. You know, the other ones that we might try on that one, boy, that, you know, it wasn't going to be an easy u prime over u. You know, there just really wasn't a lot that we could do with that original integrand, given the techniques that we had learned previously. The one thing that we could have tried, I suppose, would have been an integration by parts. But wow, man, that is going to be a whole mess of work, considering that your u is probably going to have to be the whole fraction, and then your dv is just dx. And so, yeah, good luck. It would just be, that would be a long process. Much better to go with partial fraction decomposition. Okay, what happens if the factorization of the denominator has a quadratic factor and is not a repeated linear factor? Well, then you have to use a linear numerator. So let's take a look at one like that. Here we go. I've got 2x to the 3rd minus 4x minus 8. And oh, look, they've already factored the denominator mostly for me. That was convenient. Saves us a little bit of work. Okay, so again, like I said before, I'm going to go ahead and go to some scratch paper, come back to this in a minute. So let's talk about partial fraction decomposition for this guy. It was 2x cubed minus 4x minus 8. And in the bottom here, I had x times x minus 1 times x squared plus 4. And I factored the x out of that first binomial. And so I can see the 3 factors. And since the x squared plus 4 is not a repeated linear factor, we are going to have to use a linear numerator for it. So, you know, we're going to have a over x, just like before. We're going to have b over x minus 1, just like before. But now what we have to do is we have to put a linear model or linear term in the numerator, because we're always trying to get the degree down by 1, unless it's that repeated linear factor. Okay, I should say, if you had forgotten that you could do that with repeated linear factors, and you had gone ahead and done the previous one with the x plus or x minus 1 and the x minus 1 quantity squared, and used a quadratic factor for its numerator, I'm sorry, a linear factor for the quadratic denominator, you would have found that the c would have been 0 anyway. So, so it wouldn't have mattered that you had forgotten at that point. So that's the nice thing about that. Okay, multiply the denominator over, and we're going to get 2x cubed minus 4x minus 8 equals a times x minus 1 times x squared plus 4, b times x squared plus 4. And this is probably not going to fit too cleanly on here. Cx plus d, that's going to get multiplied by x and x minus 1. I'm sorry, guys, that spilled over onto the next line there. I'll try to write smaller here as we go through. What is our convenient choice for x at first? Well, if you're thinking 0, you're thinking correctly. The 0 is nice because you can see it's x is a factor in these last 2. So we'll get on the left side here, -8. And on the right-hand side, you'll get a times -1 times 4. And so you're going to get a is equal to 2 right out of the gate. And so that's very convenient. Another convenient choice for x is probably going to be +1. Okay, because if you do +1, well, on the left side, you're going to get 2 minus 4 minus 8. So you're going to get negative 10. The first term and the last term have an x minus 1 factor in them. So they're going to be 0. And what you're going to get here is b times 1 times 5. So you're going to get negative 2 is equal to b. What happens next is we have two unknowns still to solve for, c and d. We're going to use the a and the b we've already solved for, but we still have two unknowns, which means we're going to need two equations. That's right. So we're going to have to pick two convenient choices for x. So let's pick a convenient choice. How about x equals negative 1? If you hear a rather strange sound next to me, that is my dog, and she is currently eating a yogurt container. So I know, she's nuts. All right, where were we? X equals negative 1, yeah, all right. So if x is equal to negative 1, on the left side here, you can see, well, we have 2 times negative 1, so negative 2, plus 4, so that's, positive 2 minus 8, so that's negative 6. Over here on the right-hand side, now a is 2. If I put in negative 1, I get negative 2. And then x squared would be 1 plus 4, we get 5. Okay. Now remember, b is negative 2, x is negative 1, and of course this is 5. And then lastly over here, well, remember, x is negative 1, and it goes in here too. So we're going to get negative c plus d times negative 1 times negative 2. Oh, puppy dog. All right. So simplify all this, and what you'll see is positive 2 equals negative c plus d. When you multiply all this out, you get negative 20. Multiply all this out, you get 10. Okay. Here's a positive 2, so that's how we're going to get 2 equals c minus d. We need one more equation that has both c and d in it. So I'm going to pick another convenient choice for x, and I like to keep x positive if I can, so I'm going to pick 2. And then so on the left-hand side, now we get 2 times 8 minus 4 times 2 minus 8. Oh, that's 0. That's very handy. And now remember, a is 2. 2 minus 1 would be 1. And 4 plus 4 would be 8. Minus 2 for b times x, which is 2, times 8. And again, we're plugging that in over here for the x that's a coefficient there. So we are going to end up with 2c plus d. Oh boy. Oh, guest appearance by the dog. Okay. Okay. All right, Gracie. Hello, sweetheart. Yes. Well, I don't know if I should keep this Zoom bomb in here, but this is pretty funny. Okay. This is Gracie. Yes. Say hello to calculus class. All right. Now, Gracie, you have to go. Go on. Go on. Go find a toy. All right. Sorry about that doggo interruption. Where were we? Plugging in 2. So x is 2 and x minus 1 is 1. And if we solve all this, you're going to simplify here. You're going to get 16. Okay. You're going to simplify here, and you're going to get negative 32. And here you've got 2 times 2c plus d. And so when you move everything around, you're going to get 8 equals r2c plus d. Now we have a system of 2 equations with 2 unknowns. We've got 2 equals negative c plus d, and I've got 8 equaling 2c plus d. So really, if I just subtract them, okay, you can see that I would get 2 minus 8, negative 6, negative c minus 2c, negative 3c, no d. And so there you go. C is equal to 2. Pick one of these equations and you'll get that D is going to be 4 and you're good to go. So all right, so let's put everything back together. And we get A over X, B over X minus 1, CX plus D over X squared plus 4 dx. And for the, I put plus D, I meant to say plus 4. That's funny. There we go. And so I'm actually going to split that last fraction up because I can already see how I want to integrate that. Because the 2x over x squared plus 4, that's a nice u prime over u. Okay, so let's see. We're going to have a natural log of x show up. I'm sorry, a 2 natural log of x. Okay, and then we're going to have a negative 2 times, oh my gosh, the dog is back. No, go on. I have to make the video. Okay, go on. She's been very patient with me being here all day. I suppose that one was kind of redundant to put those absolute value signs on there. X squared plus 4 is not going to be negative. Okay, what about this last one? 4 over x squared plus 4. That's 1/2 arctan x over 2 plus c. And of course, you could clean up the coefficient there. But yeah, that's a partial fraction decomposition with a quadratic factor. So, all right. There's a nice set of instructions for you on how to approach these integrals. You know, Dr. Larson is a big fan of boxes and things like that. So I would steer your attention to 516. So check out page 516 for some nice instructions. He has how you should think about going through these problems. Step 1 is always divide if it's improper. So I'm meaning the degree of the numerator is higher than the degree of the denominator. Go ahead and do your polynomial division. Whatever's left, you know, the remainder over the divisor, that's where you're going to do your partial fraction decomposition. Hopefully the other terms will be pretty straightforward to integrate. So there's a nice box there for how to do partial fraction decomposition. And then in addition to that, there's a gray box on page 512 um, that shows you, or 512, I'm sorry, 521. There's a gray box that has some pretty nice instructions for how to solve the basic equation. And those two boxes combined with whatever we've done here, hopefully will help illustrate a little bit more about partial fraction decomposition. So thank you so much, and for being patient with my dog showing up in the middle of the video. Hopefully I edited most of that out when she was trying to climb in my lap. She's a cute dog, but can be a little pushy at times, especially when she's been so patient all day long. She just really wants to go for a walk. All right, thanks for tuning in, guys, and we'll see you in class on Thursday.